Hi everyone, this is April Kaysen with GS1. This is the Innovation in Action webinar, the first webinar of the series for MIT. Give us just one more minute and we'll get started. Okay, hi folks, this is April Kaysen again with GS1. Isaac, are you on the line?
Hi, April.
Hey there. Okay, I can hear you well. This is again the Innovation in Action first webinar of the series. We've been working with the Auto ID Lab now for quite some time, and we're really trying to expose the wonderful things and projects that they're working on currently. So I'm going to turn it over to Isaac Ehrenberg with MIT so he can get started, and we really appreciate you joining us, Isaac.
Hey, thanks for having us, April. We've really been looking forward to doing this webinar. So I'm here at MIT in Sanjay Sarma's office, actually. He's not here today right now, but I'm here with my colleague, Rahul Bhattacharya, Brian Subirana, and Shane. What's your last name, Shane? Shane Pratt. We're all researchers here at MIT. We're going to present three different projects to you guys, and yeah, we hope you like it. So just to jump right in, the first presentation is entitled "The Retail Product Recognition System for Improving the In-Store Shopping Experience." Most of this research has been headed up by our graduate student Yangbin Sun, as with Sanjay as his advisor, and I've also been working with him as well. So the thing is, you know, the retail shopping environment. You need to be able to change slides. There we go. Retail shopping experience hasn't really changed, you know, too much, you know, since retail began, but it's really being challenged by the online shopping experience, and we've been looking for ways to, you know, improve the in-store shopping experience. How can we use technology to do that? Some of the challenges that exist in the retail shopping experience can be difficult to make buying decisions. You know, nowadays there's an overwhelming abundance of products that are similar. It can be difficult to make buying choices. You know, Sanjay always quotes a particular study that when people have too many choices to make, they actually purchase less things. You know, it's okay to have 2 or 3 choices, but once you have 4 or 5 or 6, it's harder to actually make decisions. And sometimes in this retail environment where you have 10 or 20 different types of olive oil to choose from, 30 or 40 different types of cereal to choose from, even different types of milk, it can be a challenge to make these types of buying decisions without some sort of external help. There are different ways that you can get help in our today's supermarkets. There's always a shopping assistant that you could go to help you make your shopping decision. There are also different places have installed kiosks, which maybe will help you get pricing information and some other information. There's some technology creeping into the retail environment, at least for the consumer, for interaction with the consumer, but it's really pretty minimal. How can we make the shopping experience better in order to help out? And the one way that we can look at making the shopping experience better for retail is to look at where online shopping has excelled and try to transfer some of those things that exist by online shopping, which are, you know, really have improved the shopping experience in general, and sort of transfer them over to the in-store shopping experience. So one thing that you get from, you know, an online shopping experience is you have the ability of the retailer to give you pointed information, you know, from what you're looking at. That information can be related products, reviews of the products, different how price of this particular product, how that depends on different varieties of that product, how price is affected by those varieties. It's accessible 24 hours a day whenever a person wants it. There are a lot of benefits that online shopping has that in-store shopping doesn't have. One of those big ones, which would really address the difficulties in making choices, is the availability of customer reviews. In an online shopping situation, especially a place like Amazon, every single product has reviews available. Those reviews are rated. Some of them are really useful, and they're the ones that you see first. Some of them are less useful, so they're put down at the bottom. You can get a very good sense of what other people, what your peers think about these products before you make a decision. That kind of customer review external help to help you make a buying decision doesn't really exist in the in-store shopping experience. It can, with the introduction of like the mobile phone and having a mobile computer on you while you're going through a supermarket. People can look at online reviews that way, but that's it's not seamless. So we've been looking at how we might be able to make that whole integration of the advantages that exist by online shopping and using mobile computing, make those things available during the in-store shopping experience. How can we make, the one question we've been asking ourselves is how can we make this in-store shopping more intelligent? Now, how can we have sort of integrate into your physical shopping cart the shopping list that you normally would have, the customer reviews that you have, the coupons that the retailers or that the brands want to make available? How do we get all of those things into the in-store shopping experience? And one of the main ways that we've been doing that is by looking at the cell phone. Now, as I mentioned before, the cell phone, this great mobile computing object, it gives you the connectivity to the internet that you need in order to get information about products, but it's not seamless. If you want a product, you have to, maybe you can scan the barcode, but as we know, there are some issues. You don't always get the right product when you scan the barcode. You can try to Google search for the particular product to see if you can find reviews on it, but it's not always seamless. Well, so what we've been looking at is ways that you can, just by using the camera on your cell phone, recognize the object that you're looking at, and then gather information from it and make that presentable to the customer in the retail establishment so that he can better make the shopping experience. So we've specifically been looking at what are the different image recognition algorithms that are available that we can use for this image recognition of retail objects, in a retail store, in order so that we can make the connection between what's in the physical store and what's available on the internet, all of the reviews and coupons and everything. How can we bridge that connection through the cell phone in a more seamless way through image recognition? People have tried this before. People have at ETH, at CMU, at Amazon, at Rochester, University of Rochester. They've all tried different algorithms with, as you can see, different percentages of accuracy for identifying the objects that they've been looking at. So we've also been looking at what kind of algorithms can we put together to have a robust, fast image recognition of retail objects so that we can enable this kind of connection and really improve the shopping experience that people have in the brick and mortar stores. So I'm going to take you through the algorithms which Yongbin has tested and worked through, and this is basically how it goes. So it's really a two-phase visual recognition algorithm. We start by taking an image of the object, and we look for different features on that object, and then we do a rough classification of, am I looking at a Pillsbury quick bread dough box, that kind of thing. And then from that situation, we take that first phase, then we go into a second phase, and we try to make sure that we're looking at the exact product that we're looking at before moving forward. Right. So what's the procedure for recognizing an object? So as your camera looks at an object, in this case again, this quick bread muffin mix from Pillsbury. So the camera takes an image, looks at the values of the color throughout the image, and then is able to find patterns in there. And from a database of images that maybe we've taken in the past, we're able to recognize which object this is, comparing it to other things and other things. So if you look down at the bottom on this particular slide, we have A, B, and C. We have three different products that we're comparing this Pillsbury quick bread to. One of them is the actual product. So there we have 65 match features. One of them, the one in the middle, is instead of cinnamon swirl, that we're trying to compare it to chocolate chip, a chocolate chip type, which is a slightly different variety. That has 53 matches. And then we're looking at something like honey cornbread, which is very different, where we have 0 matches. So in this case, this is actually one of the boundary cases where we're able to recognize that we're looking at something from Pillsbury and it says quick bread on it, but we don't know exactly what type of product it is. We know it's not cornbread for sure. We know it's not anything else in the supermarket, but we want to be able to specify exactly what it is with very high precision. And one of the problems with the image processing algorithms that other people have used is that they come to this situation and they don't know how to go further. They say, well, we're going to have a collision between these two different quick breads, so we can't use image processing in order to recognize what the object is. But in this case, we go to the second phase, where we have a general idea of what we're looking at, but then we go do a deep dive into the image processing and figure out what is exactly written on the package, and that will help us classify. So again, how exactly does this work? We first do rectify some geometric transformations from the image that we have in our database that we're using to test this against. And then we look for specific signatures on the image and try to make a match. So in this case, the thing that the algorithm focuses on is text. And in this case particular, it's the cinnamon swirl that we focus on in order to get a match. Then we can compare that to other images like chocolate chip swirl. That's not a good match. But we can compare it to other variances in illumination perhaps on the package or other things like that. And then we can train our models to be able to pick those out. So we can tell very, very well between something that says cinnamon swirl or chocolate chip swirl, and it's a very robust detection algorithm. This is a test situation of like a very crude shelf in a supermarket with a bunch of different products that look very similar, but each one of these is different. And we're able to tell the difference between each one of them using our algorithm. This is a chart of how well a bunch of different algorithms work to tell the difference between all of these products, which are have a slightly similar one paired with them. So our algorithm is the one all the way on the right side of that chart, and we're able, with 100% accuracy, at least for these particular products, tell the difference between Haagen-Dazs vanilla chocolate peanut butter versus Haagen-Dazs vanilla milk chocolate almond. And being able to tell the difference between all of these things really helps us, or really makes this image recognition viable for us to just take our cell phones, go into a retail establishment, and make the connection between an image, which is stored on our computer, and all the information connected to that image, to the actual physical product that we're about to buy. So one other issue that we looked at in terms of using image recognition to help consumers in a retail establishment is that image recognition can get very slow. When you have to take an image with hundreds of products within that image, thousands of products in your store, millions of products in your store, you have to do a lot of calculations in order to really nail down exactly what product you're looking at. So we've been looking at how using RFID can help improve that recognition speed. By putting RFID tags on all the objects, we can really limit the amount of objects that we need to look through in order to have our image recognition do what it needs to do. So the way this works is by if someone would, we're talking about the future now, where if someone has a cell phone, where they have a camera on their cell phone, as well as an RFID reader built into their cell phone, they can take an image as well as read all the tags that are in their image and only do image recognition on the objects that are visible to them. And that really speeds up the image recognition results. These pictures show the speed comparison of image recognition versus when there's RFID and when there isn't RFID. And the horizontal lines show that it always takes 2 to 3 seconds to recognize any object when we have like 60 to 100 objects. But if we're using the RFID side of the system, we can recognize those objects much faster in less than a second, as long as you only see 10, 20, or 30 objects in your visual range at that time. Once you get to more than that, then some of the benefits of RFID in this case start to slip away. But by throttling the amount of power that you're using in your RFID reader, you can really set and limit the amount of RFID tags that are visible, that are within range of being read, so you can sort of control the situation so you only read maximum 20 or 30 tags and are really able to take advantage of this. And we've been working on generating a mobile prototype. We've got a mobile phone with an app which does the image recognition. And we also have that connected to, at the moment, a USB external RFID reader. And we have the whole server set up to do all this image recognition to help us do some tests and see how exactly this will change the retail brick and mortar shopping experience going forward in the future. If anyone's got any questions about that, we can definitely take those now. April, are we there?
Yeah, I'm here. Do we need to unmute everybody? Does anyone have a question? If you do, you can just hit the chat feature for now. We don't have any on this side. Go ahead, Isaac.
Okay. All right, so that's that first project that we were presenting. Now we've got Rahul Bhattacharya is going to present the next project that we've been working on. So let me bring that up.
All right, so good morning, everyone, and thanks for giving me a chance to present. My name is Rahul Bhattacharya, and what I'm going to do today is show you our project in trying to take low-cost passive UHF RFID tags and adapt them to serve as low-cost pervasive sensors. Let me just get in there. Yeah. All right. I'd like to preface my talk by showing this picture that I found on the IBM Smarter Planet blog that captures very nicely the exponential growth in computational devices in the environment around us. Till the early 2000s, connectivity was mainly the domain of computers, but now computing devices have started getting into every aspect of our lives, from the vehicles we drive to even the clothes we wear, and that's what's called the Internet of Things. We are sort of on the cusp of this growing exponential, and I think well-established technologies like RFID, NFC, have tremendous potential to serve as sensing devices and generate a lot of useful information. So the outline for my talk is going to go as follows. First, I'm going to show you our concept of taking an RFID tag and converting it into a low-cost sensor. Specifically, we are going to use the tag's antenna as a sensor, which is why we call it the moniker RFID tabs or tag antenna-based sensing. I'm going to show you 4 representative applications from a variety of different industries. And finally, I hope to leave you with a couple of takeaway messages about the opportunity in this area of sensing, as well as some insights that we've been able to gather. So why would we want to use RFID for sensing? And there are four really compelling reasons for doing so. The first is RFID has a proven track record in a lot of industries. There are about 5 billion tags that are in play today. RFID has been used for almost a decade or more in the fast-moving consumer good and apparel industry. So, it's something that people associate with object identification, specifically low-cost object identification. Decades worth of research has led to RFID tags being available at really low prices. You can buy RFID tags in cheap for about 7 to 15 cents per tag today. Wouldn't it be great if you could take that and convert it into a 7 to 15 cent wireless sensor? The communication protocol between the reader and tag is standardized, which facilitates interoperability, which is a big thing when you're trying to build an IoT system. So that's definitely a plus. And finally, if you're a business process that is invested in setting up an RFID infrastructure for object identification, well, now you can tack on sensing information for virtually free, which is a big plus. So 4 compelling reasons. The big question is, how do you add sensing functionality at low cost? And so here's the snapshot idea of the RFID tags concept. I'm sure everyone here knows what RFID is, but just as a quick recap, the system consists of 2 components. There's the reader and the tag. The reader essentially sends out a power wave that impinges on the tag. The tag in turn absorbs some of this power and sends back ID information to the reader. So our concept is as follows. What if you could have some physical parameter of interest, say temperature, affect the tag in a controlled manner so that it manifests itself in either a drop in the signal strength with which the tag responds back to the reader, or shifts the frequency at which the tag talks back to the reader. Then, in addition to getting object identification information, you also get some very simple information about the environment around the RFID tag. A lot of RFID readers are capable of extracting these signal parameters, but most people just ignore them and just focus on extracting the ID. So they are like, well, if you're getting all this extra information, why not put something more into it? So in this case, sensing. So that's the real idea behind it. So I'm going to show you how we can do this in 4 different application areas. I'm going to talk about a crack sensor for monitoring civil and concrete infrastructure, a soil moisture sensor for agriculture, a sensor that detects anemia in healthcare, and also a fluid level sensor, which has a broad area of application. So let's start first with the infrastructure condition monitoring application. So a Senate report that came out in 2014 says that about 1 in 4 US bridges are structurally deficient. I mean, if you remember the St. Anthony's Fall bridge collapse in Minnesota, that just shows that, structurally deficient infrastructure can and have very severe consequences if they fail. Another White House report that came out in the same year says that bad infrastructure, potholes, not up to spec transportation infrastructure cost the US economy about $120 billion in 2014. So this is a pretty big problem that, definitely warrants monitoring. I'm sure each of us can relate to an example like that's put up in the figure over there. What you can see highlighted in the blue circle is a crack that's developing in a concrete arch span. The crack by itself may not be that bad, but the problem is that if the crack exists, then water and salt can get inside the structure that can corrode the reinforcement. That is the load-bearing element of a structure, and that can lead to problems. There are wireless sensors available for health monitoring in civil structures today. For example, SG Link's wireless strain sensor provides strain readings in buildings, but the problem is these sensors are pretty expensive. And concrete, being an inhomogeneous material, requires pervasive sensing because cracks can develop and propagate in different directions. So you really want to have a lot of sensors covering a zone where you think cracks may develop. So we thought, okay, let's try and see if we can use RFID to solve this problem. And so we created a slightly modified version of a typical RFID tag, which you can see in the figure A up there. Essentially, this tag consists of 2 parts. There is a straight radiating element over here, and then the IC is coupled to this radiating element using an inductive loop as so. And so the idea basically is that if you cut this radiating element because of a crack in any of the, say, middle 2/3 part of the radiating element, then it severely causes a drop in the performance of the RFID tag. And we can actually use that to detect not only the onset of a crack, but also its direction of propagation. Let me give you an example. This is a prototype that we put together in the lab on a piece of plywood. What you're seeing here is a grid of RFID tags. So here's one individual RFID tag with the radiating element and the inductively coupled IC. We make the radiating element out of a copper conductive paint that actually bonds really well to the structural surface. And then what we do is we subject the plywood to stress tests so as to sort of simulate a crack that would develop on the wood surface. And so you can see the little dotted line representing a crack that we developed in the structure. And what you see is it severs tags 1, 2, 4, and 5. And you would expect that it is hit tag 2 and 4 in its sensitive zones. So you would expect to see a drop in performance of these 2 tags relative to all the others. That's actually what we do see here. The signal strength of both tags 2 and 4 drop significantly compared to all the others. And so, this is a really easy way to implement an array of crack detectors. This is an article featuring our work on the RFID Journal, which tends to, write promotional pieces about some of the work that's going on at the AutoID labs. So check back here often. Often some of our burgeoning technologies do make an appearance on this website. The next application I want to get into is soil moisture sensing in agriculture. There is the growing population in the world, if it continues to grow at the rate that it's forecast to, by 2050, there's going to be a need to increase the food production by about 70%. And as a result of which, there's a lot of money going into agricultural innovation. Farm 2050 is one of the most prominent portals to catch up on that. And as a result of which, agricultural innovation is a $250 million annual industry today. This comes at a time when climate change and is causing uncertainty in the water patterns. There are a lot of drought-prone regions that are getting particularly worse. For example, the state of California. And so there's a real importance to monitor the amount of water that's being used in agriculture. In a lot of places, agriculture the water consumption in agriculture can be more than 70% of all water consumption. So it's a pretty big area. Also, the yields of crops are very dependent upon the amount of moisture that is received in the first top 8 centimeters of soil during the growing cycle. So in the first 3 months, if the crop doesn't receive adequate water in the first 8 centimeters of water, it can lead to bad yields. Also, a study by Correz in 2010 said that moisture patterns vary tremendously across a field. That's because of topology as well as substrata. So for example, if one part of your field has got a sandy substrata, it can drain water a lot faster than another part of the field. So there's a big case to be made for pervasive soil moisture monitoring in the topsoil of a field. So we thought, okay, let's see if we can solve the problem using RFID. And so we came up with a design that you can see in the figure over here. What we have here essentially is the standard RFID tag with the antenna and the IC. But in addition, we also have this little structure called the monopole probe that you can see that's being inserted into soil, which is sand in this case. And the monopole probe, essentially, you can think of it as sort of like a variable capacitor. And so if you're putting it in dry or wet sand, that capacitance is going to change. And in turn, that's going to affect the tag in a controlled manner. So let's take a look at an example. So if you look at the figure over here, please just focus on the green curve. What happens is initially we've got a system where the sensor is put in dry sand, and it's designed in such a way that it responds to a very strong signal when it's put in dry sand. However, as we start adding water, 100 ml, 60 ml, and then another 40 ml, the tag gets completely saturated and then you don't see it anymore. So that little wavy line at the -55 mark just indicates that you're not picking up the tag anymore. And then over time, as the soil dries out, the water disperses through the sand medium, you start seeing the signal strength coming back to the original state of the dry sand. And so basically just looking at this, you can get qualitative estimates of whether the sand is dry, saturated, or perhaps somewhere in the middle. Here is an article that the New York Times did by interviewing Sanjay about this technology. And in addition, our idea also won best paper at the IEEE RFID TA conference in Japan just last year. All right, the third application that I want to get to is healthcare. And specifically, we're going to talk about the design of an anemia sensor. So what is anemia? Anemia is a medical condition where a person has a lack of oxygen intake because of a reduced red blood corpuscle count. It's a pretty prevalent problem, especially in the developing world. About 41% pregnant women and 47% preschool children classify as anemic. Why is this a problem? Because if you don't get enough oxygen in those formative years, it can impair cognitive and physical development. Many times it is indicative of more severe issues, for example, malnutrition, parasitic infestation, or bacterial or viral diseases. Anemia can be measured pretty reliably today by using a centrifuge. So what you do is you take a blood sample, you put it in the centrifuge machine, the centrifuge separates the red blood corpuscles from the plasma, and by looking at the relative volumes, you can figure out whether someone is anemic or not. The problem is that centrifuge is capital equipment, and so if you're trying to do this in a remote part of the world where you may not have access to a centrifuge, transporting the blood samples to the next big city is going to be a challenge. And so we were saying if we could do this in a way that you could automate the process in the field automatically. And so we decided to make use of a paper-based design to solve this problem. So what you're looking at here is a cross section of a piece of paper. And what we do is we divide this paper into two zones. There's a plasma separation boundary that's marked. And what you do is you seed the right-hand side of the paper with a blood sample. Now, if someone is anemic, for a given volume of blood, there's going to be more plasma per unit volume than red blood cells. So that plasma is going to separate out because of osmosis and travel straight down the rest of the channel at a pretty fast rate. On the other hand, if you have someone with healthy blood, then there's less plasma per unit volume to go around. And so that's going to go out on the left-hand side at a much slower rate. And so you can relate the rate of propagation of plasma down the rest of the paper to red blood corpuscle count. So it's a very simple idea. Now the question is, okay, this is great, we've done it for paper, but how do we adapt this to be an RFID sensor? And so we do it as follows. We make use of a monopole probe design that you can see in the figure over there. So if you look at the inset figure in the top right, there's your typical RFID antenna with an IC, and in addition, we have a little channel, which is where you're going to be measuring plasma. And I've just blown up that channel, which is slightly modified in the bigger figure over there below. And so the idea is you put the sample blood in the zone, the little green line represents the plasma separation membrane. The plasma is going to separate out and it's going to cause a predictable change in the RFID tag's response. So how does this work? So here's how it works. So if you put the blood sample in the zone S1, initially the tag is responding with some signal strength, in this case -35 dBm. The plasma starts separating out. As soon as it touches the metal part in zone S2, it causes an initial drop in the signal, which you can see over here. Then as it starts propagating all around the curved channel, the tag doesn't get affected because it's not touching any metal. So you can see that the signal is pretty steady at S3. And then finally, when it touches S4, you suddenly start seeing the signal strength drop again. And then by the time it goes completely under 4 and reaches S5, you've sort of stabilized again at S5. And so if you start timing things when the first signal strength drop happens, and when you stop timing either when the signal starts dropping again at S4 or has stabilized at S5, you can try and relate that to a red blood cell count. And so here's some results that we got in the lab. What you can see here is the variation of the flow time as a function of red blood cell, which in this case is hematocrit percentage. A person who has 20% red blood cells per unit volume is classified as anemic, and someone who has about 40 is classified as healthy. We did this for 4 repetitions just to make sure that we are getting repeatable results, and in fact we do. We can very confidently differentiate between a anemic person and a healthy person. This here is just a news article recently featured on this technology in RFID Journal, and I'm going to be giving a talk at RFID Journal Live in May in Orlando. So if anyone happens to be there, please do feel free to stop by and listen to my talk. So the advantage of this technology, you get quantitative results by which you can relate anemic, degree of severity of anemia to a flow time change. It's amenable to large-scale automation. So, for example, if you go rapidly screen about 100 people, seed tags with blood samples, put that in front of an RFID reader, you can automatically detect who's anemic and who's not. And furthermore, since you're using RFID, which has a globally unique identifier, you can quite easily tie that blood test to a person's electronic health record, which is great. So that brings me to my final application of fluid storage, fluid level sensing. There's a lot of places where fluid level sensing could be useful, and frankly, it's one of the simplest sensing that you can do with an RFID tag. A very good example is in monitoring wet cells. So a lot of data centers have batteries like this in case of a power failure, so that your computing operations don't get interrupted. It's critical that the acid concentration inside these batteries is not too dilute and not too concentrated, because then it starts compromising the battery's performance. And so the right level of acid concentration is monitored by monitoring the fluid level inside these batteries. So that's one great application of fluid monitoring. Also, interestingly, high-end liquor inventory in bars. At the end of the day, you want to figure out automatically and rapidly how much high-end liquor is still available in your inventory, and if you need to go ahead and do more ordering, that's something that is a good case for fluid level sensing as well. And so we thought, okay, let's try and see if we can develop a low-cost fluid sensor, but we wanted to do something slightly different. Up till now, I've been showing you applications where we've been manipulating the RFID tag signal strength. What if we manipulate the frequency this time instead? And so what I made use of was a T-match RFID antenna, which you can see in the figure below. Essentially, this is a great design because there are only 4 parameters that you really need to play with in order to completely characterize the frequency performance of this antenna. The length of the antenna L, the width W, the width of that little slot S, and the position of that slot S relative to the top of the antenna. So it's very easy to design and simulate. So we came up with a design as follows. If the tag has no fluid behind it, that is, it's mapping a dry state of a container, then it's a broadband tag, and so it responds in all frequency in the 902 to 928 megahertz spectrum for US RFID operations or North American RFID operations. But if on the other hand you fill this up with water, then it becomes narrowband and you only pick up the tag in a very tiny band around 920 to 928 megahertz. And so by looking at this frequency spread, you can figure out whether there's fluid behind the tag or not. And so, yeah, that pretty much brings me to the end of my presentation. The main takeaway points that I wanted to leave you with is there are a lot of really cool applications that you can enable by combining RFID with smart materials, or by designing innovative antenna constructs that, like for example, the crack sensor design, where we used a little radiating element coupled to an inductively coupled IC. You can enable a lot of really interesting applications. And there are at least 2 parameters, amplitude and frequency, that are currently discarded by an RFID reader that you can sort of encode sensing information into. So you can get some additional information in addition to just the ID. And off late, RFID readers have also been offering phase, so you can start measuring things like subtle motions of the tag or displacements and things like that. So it'll be interesting to see what other applications you can enable using this 3rd parameter. And so, yeah, that's all I really wanted to say. I'd like to introduce the next speaker, Shane, who's going to be presenting some work in home automation using RFID. So take it away, Shane. Thanks.
Hello, I'm going to be talking about the IoT office. We wanted to prank our Professor Sanjay using RFID, as he really enjoys RFID and it's a real big interest of him. So we built an RFID system that detects events using RFID tags. And we can use an RFID tag basically as a simple on and off, like a wireless on and off switch. Here's a video of the office.
Listen closely. Some of the audio is not that great. It's just a home movie that we took.
Isaac, this is Deepan here. We have no audio coming into the webinar.
All right, Deepan, can you hear me?
Yes, Isaac, we can see the video, but we cannot see we cannot hear any audio.
Okay, so let's figure out how to do that. Give us a second. We'll go back to the beginning. So it's only taking audio from my... All right, so we'll just do it on the fly. Okay. Give us a second. 1 second. Pause.
Okay, so as I walked in, the RFID reader picked up the tag that I'm carrying in my hand and turned on the lamp here in the front, and then also says we have some speakers in this office that say out hello Sanjay, because that tag belongs to Sanjay.
For those of you on the phone, what we can do is after this call is over, we can send out that video as well.
Okay, here I'm about to, there's an RFID tag that we made that is, it's 2 RFID tags with a steel plate in between. And so when it's on the desk like it is now, the RFID reader can only read one of the tags. It can't read both of them. And then when I flip it, the RFID reader picks up the change in state and tells the light to turn off, like it just did now. Okay, so in this setup, every single one of these cupboards has an RFID tag on it on the top. And as the doors are opened, you can read the tag. When you close them, because the cupboard itself is made out of steel, it shields the tag so the RFID reader can't read it. And so we're showing a demo here where I open the door and the system says, it says file cabinet open. But then when I move Sanjay's tag from the room, the system realizes that he's left by turning the light off. And then when I open up the cupboard the next time, it says unauthorized access of that same cupboard. So here I'm basically just showing how simple that exact system is for those cupboards. There's literally just an RFID tag that has been stuck on top of drawers and cupboards and that. And because the cupboard itself is made out of steel, as soon as the tag is pushed in, it's shielded. No, that's it.
All right, so this video is available on YouTube, for the whole world to see. So we'll send out the link for this after the webinar is over. And now we'll just continue to the next slide.
Okay, so here we're showing an overview of our new lab. This is no longer Sanjay's office, but in our lab we're working on basically using some of Rahul's tags that he's designed, as well as some of our own, to detect different things in a room. So in this case, you can see we have a water cooler that we've mounted a couple tags on. There's a total of 5 tags, and then it shows up on our UI how much water is in the tank. As you can see, the UI represents how much water is in the tank. We also have a sensor, which you can't really see, but it's basically just an RFID tag that's on a piece of paper, and that's shielded when the AC is off, but when the AC blows out air, it lifts up the tag, and you're able to pick it up. And on the UI, that little symbol starts to spin when the AC is on. The next couple that we've built are ones that go on doors. And we found that there was we can't confidently say that a tag has disappeared. So when a tag is shielded, it's actually really hard to tell that it's really gone, and not just that the reader is not picking it up for a couple seconds. So most of our sensors have dual actuation, where when the door is closed, in this case, we see one tag, and then when the door is open, we see a different tag. And so on the UI, you can see how it looks. The one door that's at the bottom is got a red box around it and shows that it's red, which means the door is closed. And the other one at the top is telling us that that door is open. And then the third one is we have sensors on our coffee machine, which tell us how much water is in the coffee machine, as well as there's one sensor at the back which tells us every time somebody puts in a new Keurig capsule. Okay, so the RFID reader we're using is a Speedway Revolution, and the main reason for that is because it supports 4 antennas and supports LLRP, which is the low-level reader protocol, and that is an IP-based protocol. But it has a really big downside in the fact that you can only connect one client to one RFID reader at a time. So what we built was a system that takes the LLRP data and converts it into a JSON string, which we then send over MQTT. And as you can see at the bottom, this is the JSON string that we send out, which includes the EPC, the antenna RSI, which antenna was picked up on, the channel index, and then a time and date stamp of when the RFID tag was scanned. Then take that MQTT data and we process it. And in the case of the Sanjay's office experiment, we basically just check to see if a tag hasn't been seen for a while, and if it hasn't been seen, we send out another MQTT message that says this tag with this EPC is connected. And then if the tag hasn't been read for an X period of time, because we can change that depending on the exact sensor, it then sends out a message saying the tag's been disconnected. And the main reason we used MQTT instead of LLRP is for that exact reason, that LLRP only supports one client. With MQTT, we can send this data to hundreds and thousands of clients where they can analyze and use them for different things. So in the case of Rahul sensors, we can use one RFID reader for using it for sensing like we are, but as well as sending Rahul the data that he needs to run his sensors. And then we just simply have a system that receives those last MQTT messages, which tell us whether the tag's connected or disconnected, and then that actuates the text-to-speech or turns on relays, which turn on the lights and other things like that. So the main reason we found doing this is that the price is a lot lower when using RFID, especially at scale. So With conventional means of sensing a door, let's say a conventional conventional home alarm system, you're looking at about $4 per sensor, and that excludes installation, which ends up actually being a lot more. You can also go the same route using conventional like door sensors, which are generally just reed switches, using wireless, and that also is like $30 per door. And whereas RFID, we're able to do it for about 20 cents per door. We do have this massive fixed cost of the reader, in our case, the Speedway Revolution, which are like $1,000 reader. But we found, as you can see in the graph below, that as soon as you have about more than 200 sensors, it becomes way more cost effective to use RFID. And then in that sense, we can use one RFID reader to detect lots of things, not just doors, whereas the other conventional systems are generally specific to that one. Their fixed cost is set to that one door or two doors. The installation of RFID tags or RFID sensors is extremely easy as you just stick it on. We found the reliability to be quite good, and then latency was our only main issue, and that is that it takes a while for the readers to pick up tags or to notice where the tags have disappeared, but we're working on that to improve that. Any questions or comments?
So this concludes the third project. So we presented 3 different projects. One is like how we can use image recognition to change or improve the retail shopping experience. The second one is RFID tags. How can we use RFID tags in an interesting way and to sense the environment around us? And that was really expanded and really demonstrated by Shane in the IoT office example, where we use tags in not just to inventory things on a shelf, but to tell us the state of different objects around our office, around Sanjay's office. So I guess that concludes really our presentation here. If you have any comments or questions, ideas that you thought up with, I actually see a question that someone sent. If anyone else wants to speak up now, though, feel free.
Yes, if you have a question, please raise your hand on the dashboard, and we will unmute you.
Okay, so we've got 2 questions that I can see. Question 1 was, okay, I don't remember exactly when these came up. But actually, so one question, Deepan or April, anyone there?
Yes, Isaac, there were 2 questions received. The first one is from Dennis O'Brien. I'm just going to read out the question for you. This is in regards to your first presentation on the shopping experience. The question is, would this be an appropriate use case for beacon technology? Would using on-shelf beacons to identify a shelf location access the store planogram to identify the products on or near that shelf? Would this remove the need for image recognition?
So I think that would just help the case for image recognition. It will help it would maybe remove like the RFID side of it. So we used RFID in this case to limit the number of objects that were visible or that we would need to search through in order to do a proper image recognition. The beacon situation, you can have a beacon on each shelf or a beacon on each aisle, and that could limit the the situation that you're looking at to only this aisle. And that would help image recognition a lot and make it a lot faster. But it wouldn't necessarily bring you the same ability to identify and get information about exactly the object you're looking at right now, the way the camera would.
Great. Thanks for answering that, Isaac. The next question we have is from Luke Boltman. And the question is, again, on the image recognition topic. The question is, has the Digimarc invisible barcode technology been evaluated as well?
So yes, we have looked into that. We have looked at that technology. So really, it's a fantastic technology. I don't know how. It's a very, very good technology, and I can't really. It has its applications where it's going to work very well. If someone didn't want to invest in Digimarc. This could almost be seen as an alternative. If someone didn't necessarily want to invest in finding a digital watermark for every single object that they've got, they could still do quite a bit with image recognition alone. But this is not to take away from Digimarc capabilities. It's really fantastic technology that they've developed.
Thanks, Isaac. One last question is here. Go ahead.
Go ahead, Deepa. I'm sorry.
No, April, go ahead. That's about it. If there are any other questions that anybody else has, please feel free to raise your hand and we can unmute you. Or you can even type your question in the chat window, and I can announce the question.
Well, right now we're at the top of the hour anyway. So first off, we want to thank Isaac and all of the researchers that are on the call today that took the time out to present this awesome information to us. Also, as a reminder, if you're not currently on the GS1 Innovation platform, which is the new EndZone, you can reach out to me directly. We will have a space for Auto ID Labs so that you can follow the researchers and the work that they're doing. So if you have any questions directly for any of these folks or any of the projects that you've heard about today, if you don't have this information, if you haven't taken a screenshot, we will get the presentation out to everyone. We will also try to send you the link to that YouTube video as well. Again, all this information will be posted in the EndZone, but if you have any questions, please reach out to one of us directly, and we do appreciate you taking the time out of your schedule to present to all of our users, as well as we appreciate you taking the time out of your busy schedules today to join to hear the fantastic work that MIT is doing. Thank you very much for joining. I hope you guys have a great day.
Thank you.
Thanks, Isaac. Bye, everyone.